the less elastic. So if you can consider your parametric values or set of the values which is not experimentally or which is not really good for your problem, then the first question will come that why you have considered these things. So all these things when you consider in your mind, then your paper or the writing of the paper will be very good. Then again the last, because when the editor is satisfied with the abstract, they will not go the rest of the part, they will see the conclusions or concluding remarks or key points of your work. Okay, and that is very much important. So whatever the discussions you have done in your analysis for your results, what type of novel findings are there in your results or in your discussion, you summarize in 4 to 5 sentences in a conclusion. That is more than enough. And when you find out the good paper, the conclusion will be 3 to 4 lines or 5 lines maximum, and abstract will also be 4 to 5 lines. You just go and read the paper, good paper. I have given some journals, like you can see the journals of Royal Society, you can see the journals of Nature, you can see the journals of AIP, IEEE transaction, you can see the journals of AIP, American Institute of Physics, and find out what type of papers people are. And again another things, you select reading of the papers of some particular group, because there are some groups in your field who are working very well. Suppose I am working in the biofluid, I have to choose a person or group who are working very well in the particular fluid dynamics or biofluid dynamics, and reading their papers is always giving the good knowledge as well as giving the good ideas and giving the good problems. So you try to select some groups, and also in the literature you cite their paper only, because if you choose the good groups and download the papers of there, you can see that in their papers, every papers, some new things will come. And when you read the papers where the new things are coming, you can develop the new ideas. And when you have new ideas, or there is a chance, or there is a possibilities to extend or to work on that particular paper, your paper will be more applicable. So these things are basic knowledge which I gained from my experience. I have shared. Now we'll come to the, if you have any doubts or discussion or any confusion, you can discuss. We have 3 to 4 minutes. Chai tayar hai. Then we have the tea break. Okay, and then we'll come to the lecture which I am delivering everywhere. Okay, and we'll come to the basic concept of the fluid dynamics, biofluid. So all this experience I have shared. Many experiences are there, but I don't have much time. Okay, and sharing the experience, because many learning processes are coming from the experience. Okay, sometimes missing the flight, sometimes traveling with different type of people, sometimes sharing the room from the different type of roommate. Sometimes you can learn many things from working with different type of supervisors, different type of teachers, different type of friends. So everything is a learning. Okay, so when you learn many things from the experience, you can have. So whatever I have learned, very briefly I have explained. Okay, if you have still any doubt, you can ask. I will be happy to elaborate or discuss more. No? पूछिए, because this is the discussion. अभी जो प्रोफेसर अनुज आएंगे, he will talk less and discuss more. So deliberation will be there. So when deliberation will be there, then it will be more. So if you have a specific question, a specific doubt, you just ask me. What I have learned last 20 to 25 years, I will be happy to explain in very, very beautiful manner. Okay? Because I have worked in south, north, west. I am from east and also studied from east at Kharagpur, BHU, belong from the BHU, Banaras. Okay, so many experience I have learned. So whatever the things in your mind, even in the life also, I work as a Dean Student Welfare as in NIT Uttarakhand more than 4 years, 4.5 years. One tenure I completed as 1.5 years. Second 3.5 years I have completed. Now I am looking the research consultancy. One tenure I have completed more than 3 years, and the second chance again I have been allotted. Second again I am discharging the research and heading the research consultancy department. So I have learned many things. I have also discharged as a registrar for NIT Uttarakhand for 2.5 years, which is more challenging part, but I have learned a lot. So when you take all the responsibility, many things you can, and now you can see that even you can ask with my student, I am always smiling. Whatever the problems are there, always smiling. Okay, and easily trying to solve the problems. So many students, I have worked as a counselor also for the student, counseling to the student. If they are in depression or anything, you can sit with me and discuss many things friendly. So don't worry about the life. You enjoy the life, learn many things, and there is a very good mantra that hard working. You have to be hard worker if you really try to become the happy. खुशी आपको तभी मिलेगा जब आप ज़्यादा से ज़्यादा काम करेंगे. जितना आप काम कम करेंगे उतना ही दुखी रहेंगे, और जितना आप दुखी रहेंगे दूसरे को दुखी करेंगे, और जितना ही दूसरे को दुखी करेंगे उसका जो है डबल आप फिर दुखी होंगे. ठीक है, तो ये सब चीज़ें आप ट्राई करिए. कुछ और पूछना है तो ठीक है, अदरवाइज थैंक यू. We'll end or conclude this session and we'll come again after 5 to 10 minutes for second session. Thank you. Again, that I said. Next session will be the technical, and we will start the fluid dynamics approach and how we are using the fluid dynamics tools for the various applications. So first, the concept of, as I told, that before starting any problems or research work, we should have the knowledge of basic. So what is the fluid mechanics? So fluid mechanics is a subject, and when we have to work on the fluid mechanics problem or fluid dynamics problem, or think about the application, we should understand what is the fluid mechanics. So again, fluid mechanics is having the two different words. Okay, one is the fluid and another is the mechanics. Fluid means the material, and in the nature, whatever you are looking, or whatever things are visualized easily, everything is a material. Even our body is also material. The things surrounding the classroom, everything is the material. And material is having the three different states. You know, one is a solid, liquid, gas. So when we take the two different state of the material, like gaseous state and the liquid state, that is the fluid. Solid is different. That's why there are again two subject. One is the solid mechanics, and another is the fluid mechanics. So in the fluid mechanics, the two different state of the fluid, liquid and the gaseous state we are studying, and in solid mechanics the solid state of the material we are discussing. Simply when we define the fluid as a very beginning level, people are defining in the form of that the material or the items or the object which are having the tendency of the flow. That is the fluid. But the actual definition is different, and we can define the fluid like when we apply the force or when we apply the stress on any material. If there is a deformation, if there is a change in their their position, then that material is a fluid. So it is only applicable when we apply the force, and if there is no deformation, that is a solid in nature. That means more elastic. So when the elastic property will be dominating as compared to the viscous property, then that material is categorized in the form of the solid. But when the viscosity is increasing and elasticity is decreasing, okay, means the viscosity is dominating over the elasticity, that is the liquid. And when the compressibility means the change in the density with respect to the any external force will be there, then that is the gaseous state. So three different states we can define in three different ways, and the fluid is nothing but it is just the deformation of the material under the external stress or force. And if it is there, then it is fluid. And based on the compressibility, if it is incompressible in nature, it is the compressible fluid. If it is incompressible, means there is no change in the density while applying the forces, that is the liquid. So when you compress this liquid inside the water, you cannot find there is a change in the density of the water. So the density of the water remains same, even though you apply the various forces or huge amount of the forces. But in the case of gas, you can, when you apply the force in the gas, you can compress the gaseous state. And the compressibility, if the gaseous compressibility is more, you can change the changes or transformation between the state. Like when it is very low temperature, then it will be the snow, okay, or it can be in the solid nature. If it is some average level temperature, okay, some range of the temperature, it is liquid, and when it is high temperature, it can take the gaseous state. So various material are having the different state depending upon the temperature, depending upon their nature, or depending upon the rheological properties. So when they are having the rheological property, whether what type of property, whether viscosity is more, or elasticity is more, or surface tension is more, okay, or other properties, diffusion in the liquid or any fluid is changing. So depending upon different properties, different nature, you can define the fluid. So this is one part. Another is the mechanics. Mechanics is just study the any object in the form of whether the object is at rest or in motion. If it is motion, it is dynamics. If it is at rest, it is static. So in the fluid mechanics, we study the fluid statics, and the fluid dynamics. So fluid statics means the study of the fluid at the rest position. Fluid dynamics means study of the fluid in the motion. Like one of the example I can give, the water is inside the bottle, so there is no movement of the water. So whatever the buoyancy forces or different forces acting on the water, that is the case of the hydrostatic. So hydrostatics and the hydrodynamics are the special case of the fluid dynamics and the fluid statics, where the fluid is considered as the water. So when the analysis of water is there, that is the hydro. Okay, that's why you can see the hydropower, many hydropower converting from the flow of the water to the mechanical energy, and the same energy can be converted in the form of electricity, and we are receiving the electricity in the different part of India, everywhere, from the hydropower. So when it is at the rest, but when we fit one tab in the water, if we use another tab, and tab is having the wall, like you can open or you can close. When it is closed, then it is again rest. If it is open, then water start flowing. So that is the case of the fluid dynamics. Okay. So how you can understand the concept of the dynamics and the statics? When you have some example, you try to relate your concept with the example so that the concept will be clear. So when we use the fluid and the mechanics, both, that is the fluid mechanics. And the different part of the fluid mechanics, like you can see the different state, gaseous, liquid, statics and dynamics. And the statics means what? Means it is the equilibrium position, there is no motion. So the forces apply with the different direction, this direction, this direction, this direction, this direction, this direction, everywhere the liquid is in equilibrium position. So some of the force will be zero. But if there is a change, like when you make the tag and then gravitational force will be dominating, then flow will start due to the gravitational force. So when there is a, but now the shearing and the gravitational force, buoyancy force, many forces are acting on this. So the sum is zero. When sum is zero, then it is equilibrium position, and that is the case of the. So when you define the things basic, you have to be very clear. And now you can see the definition of classification of the fluid and the flow with a different aspect. Different aspect means different properties. When we have the different properties, we can define the fluid in different way. Like when we consider the compressibility, compressibility one is the physical parameter, and based on the compressibility, we can define two different type of fluid, which is one incompressible and another compressible. So in the textbook, you can only find the two different type of fluid based on the compressibility, but another type of fluid you can see, which is a quasi-incompressible liquid. Quasi-incompressible liquid means when you are applying the force, if there is a change in the density, then it is the gaseous state. If there is no change in the density, it is the liquid state. But if there is a very slow change, which is not considerable or which is negligible, okay, then that state is a quasi, means in between the. If there is a change which can be measurable, if there is a change which can be measurable, that is the gaseous. If there is no change, then it is a liquid. But if it is in between, that is the quasi incompressible or quasi compressible, both. Like semi open and the semi close, both is same. Okay, whether it is closed from the right hand or left hand or this. So same thing you can define. So another type of, so when you see the literature, you can find such, then based on the viscous behavior, you can define Newtonian fluid as well as non-Newtonian fluid, and it is based on the Newton's law of the viscosity. Okay, those who are working in the fluid dynamics, please listen very carefully. Okay, most of the things will be very clear after this lecture. Okay, so when the fluid is classified based on the viscosity behavior, means whether the viscosity is there for the liquid or not, then you can define. And the viscosity behavior is defined from the Newton's law of the viscosity. Newton's law of viscosity means when you apply the stress, if there is a linear deformation in the material, and when you plot the graph for the stress and the rate of strain, means rate of deformation, that is also known as the velocity gradient, and you can find out if there is a linear relation then which is also passing through the origin. Means mathematically it is just like a y is equal to mx. Okay, and when you can see that the relation like from the initial level, means when we apply the force very beginning, deformation can be seen. If deformation cannot be seen, then there is a plasticity that will come later. And if there is a deformation from very beginning, very initial level, then you can find out there is a highly viscous, there is no plasticity, deformation is there, and it is in linear in nature. So that type of fluid is known as a viscosity, and Newton's law of viscosity states that stress is directly proportional to the rate of deformation. And if stress is directly proportional to the rate of deformation, that means as per the mathematics, if there is a relation of proportionality, another constant will come. And when constant will come, that constant in physics will be the some physical parameter. So when tau is proportional to the gamma dot is representing the rate of strain, then this mu is another proportional constant which equate the equation tau is equal to mu gamma dot, and mu is the proportional constant and mu is representing the viscosity nature. So the fluid, the viscosity of the fluid will be measured by the viscometer, and this viscosity is representing that how much liquid is having the viscous in nature. So based on that viscosity, you can define the fluid as a Newtonian, and if there is a change in the deformation, like if deformation is not a linear, if deformation is a non-linear in nature, like when you apply the force and the deformation is a non-linear. So how mathematically you can define? You can define that tau is proportional to the gamma dot to the power n. So n is the fluid index or the fluid property index, which is representing that the behavior of the fluid or the behavior of the viscosity, and you can find out when n is equal to 1, it is linear. So there are another two cases. Another two cases as a mathematician, how we can describe n may be greater than 1, n may be less than 1. So when n is greater than 1, that means fluid is having the thickening property or thickening behavior. When n is less than 1, then fluid is having the thinning behavior. That means fluid is a shear thickening fluid and the fluid is a shear thickening. So all cases when you consider together, that model is known as a power law fluid model. So power law fluid model is a non-linear model because it is mathematically non-linear. That's why tau is equal to mu gamma dot to the power n will be the non-linear in nature. So based on the viscosity, based on the Newton's law of the viscosity, you can categorize the fluid in the form of Newtonian fluid and the non-Newtonian fluid. In the non-Newtonian fluid, again there are another possibilities. What is another possibilities? Another possibility is if the line, your line, straight line is not passing through the origin. So it can pass through other portion of the y-axis. So when it will pass through the another portion of the y-axis, that means physics behind that means when you are applying some force up to some certain level, there is no deformation. So if there is no deformation, that means there is a plasticity in the nature. So if there is a plasticity behavior in the fluid, that means we have to go up to the threshold level or yielding point. After that, you can find out the deformation. So that point is known as a yielding point. That point is known, whatever the stress at that point, that stress is known as yielding stress or threshold value of the stress, where the deformation, and when the plasticity and the viscosity, both behaviors are there in the material, any material, that material is known as a viscoplastic material or viscoplastic fluid. If we consider simply fluid, then that is the viscoplastic fluid. So what will be the mathematical expression? Mathematical expression will be tau is equal to mu gamma dot plus some value, constant value, and that value will be the plasticity nature of the fluid, or that is the yielding stress. So tau is equal to tau 0 plus mu gamma dot will be the linear model for the viscoelastic material. It is just like y is equal to mx plus c, means it is the line of straight line, equation of straight line. And the same thing you can find for the Bingham plastic model. So Bingham plastic model is a linear viscoplastic fluid model. So viscoplastic fluid model linearly you can define as a Bingham. And if again you can think about if the deformation is non-linear, then thickening behavior as well as thinning behavior will be in addition to the viscous plus plasticity. So what will be the generalized model? You can consider tau is equal to tau 0 plus mu gamma dot to the power n. So again the n will be the fluid index, which is representing the thinning and the thinning behavior. Tau 0 will be the representing the plasticity behavior, and the mu is representing the viscous behavior. So see this is the mathematical equation, or this is the physical equation where you can mathematically relate, you can geometrically represent, and you can physically represent. So any equation where you can describe mathematically as well as geometrically as well as physically, then the concept will be very clear. And then you can think the different model. So as a mathematics people, you can relate tau to the power m, tau 0 to the power m, a more generalized form of the relation, but that mathematical equation will not be applicable for the material which is not satisfying your expression. So first you have to check the data of any material. So when you have the experimental observation, like when you are applying some stress and the deformation is coming, you can make the table for stress and the rate of deformation and see the relation. So that will be the particular mathematical. Then when you have the table or data, then what you can do, you can interpolate the data, find out the function, and that function will be the model for that particular material. So that is the way of the modeling. Like when you have any particular data from the experiment observation, and when you are interpolating the function, and if that interpolated function will work for some other type of material, so that will be the model. And same thing, it is the vice versa. Means you can start with the mathematical approach and validate with the experimental data, or you can start with the experimental data and the model as a mathematical expression or mathematical formulation. So if both are satisfying, that is the validation of your model, that is the validation of your experimental result, and that will be the more impactful work for your research. So this then we can define based on the idealization. Idealization means we have the ideal fluid as well as a perfect or natural fluid. So whatever the fluid you can see in the nature, okay, every fluid is a ideal, every fluid is a perfect or real fluid. But if we imagine that there is a fluid which is not having any physical property, means it has no viscosity, it has no elasticity, it has no other property, then that type of imagination from mathematics people can imagine, okay, and that imagination will be the imaginary fluid, and that is not existing in the nature. So when there is no existence of such type of fluid, that fluid is known as the ideal fluid, and the fluid which is existing in the nature, that is known as a real fluid. So based on that you can find out another category. Then you can see based on the homogeneity, whether the mixing of the liquid or mixing of the properties are there for the liquid, then you can define the fluid in the form of homogeneous fluid and a heterogeneous fluid. Examples are there. You can just read and see that what type of fluid can be homogeneous in nature, what type of fluid can be in heterogeneous in nature. Then based on the miscibility, like when two different type of fluid are mixed, if it is completely mixable, okay, then it is miscible fluid. If it is not, examples are there like water and milk. If you consider, it can be when you mix both, it will be the case of, for example, of miscible fluid, and when you consider the water and the oil, then it will be the case of, for example, of immiscible fluid. So based on the phase, like different layers of the fluid you can find out, like in the one chemical or 3-4 chemicals when you mix, it can be in the layers. One of the example you can see in the blood, like there are several layers of RBC, WBC, plasma, okay, and these are the different in layers. So that is the single phase. If it is only one layer, then single phase. If two layers, two phase, three phase, four phases can be seen. So multi-phase fluid and a single phase fluid you can define. Then based on the thermal properties, if there is no change in the temperature, means iso. When the iso will come, means it is the same throughout or constant throughout the different composition or different reaction or different mechanism. If you are applying any type of force, any mechanism or chemical reaction, if there is no change or if the temperature will constant throughout the whatever the mechanism or experiment you are doing, then that type of fluid is known as isothermal. And the opposite, if there is a change with respect to the temperature, then you can find out the different types. Then the steady and the unsteady, both in the physics, most of the times we are considering the time as a variable or time as a parameter in our problem. Sometimes we are not considering because the difficulty and the complexity when you are including the additional parameter or additional variable in any mathematical equation or differential equation or algebraic equation, handling that parameter with that non-linearity or complexity or linearity or addition of the one parameter. Suppose if there is a single independent variable or two independent variable or three independent variable in your differential equation, how much complication will come, and handling or solving that type of problem is again the challenge. So when you consider the time in your problem or flow analysis, that is in transient in nature, and that type of analysis is known as the unsteady problem or non-steady problem. But when you are not considering the time parameter in your problem, that problem is known as a steady. Means only the coordinate system or spatial coordinates are there, but time is not in our consideration. So when time is not in consideration, that means that analysis is a steady analysis. So steady analysis or transient analysis are everywhere, not only in the fluid, in other type of physical phenomena or physical analysis or chemical analysis, you can consider or you can give this name nomenclature. Okay, so when the flow in between, again the another type of flow we have considered, that is the quasi steady or quasi unsteady. So again, because the flow is changing or flow are depending upon the time, then if it is depending upon the time, it is unsteady. If it is independent of time, it is steady. But if there is a change which is again not considerable, if there is a small change or if there is very slow motion, slow flow with respect to the time, then that is the quasi. So these three different type of flow nature you can define. Then again uniform and non-uniform, again depending upon the velocity. If velocity remains constant throughout the flow regime or throughout the pipe, throughout the channel, throughout the vessel, okay, then it is a uniform. If there is change in the velocity, then it is a non-uniform. Or if the geometry is non-uniform, there is a possibility by using the Bernoulli law, you can see that if at a different point, if the cross-sectional area different point, if the densities are changes for the fluid, then as per the continuity equation, as per the Bernoulli law, you can find out the velocity will also vary. So when velocity will vary, then that is the case of non-uniform. So you relate every equation with the physics and then try to find out what type of nature are there, and then you can see that based on the pattern of the flow, based on the pattern of the flow, you can define whether your flow is laminar in nature, whether your flow is a transition layer like from laminar to turbulent, or whether the flow is turbulent in nature. So pattern means if there is a flow of the fluid particle, because fluid is constituted from the different molecules, fluid molecules or fluid particles. So there is a path of the fluid particle. If there is a path of the fluid particle, that path you can consider in the flow or fluid dynamics as a streamlines. And the streamlines, if the pattern of the streamlines will be parallel and very smooth, if they are not in zigzag in nature, or if they are not intersecting to each other, then it is uniform, or it is laminar in nature. But if there is a possibilities of zigzag motion, or if there is a possibility of intersecting their path or disturbing to each other, then means it is a transition. And if there is a possibility that every fluid particle is disturbing to other fluid particles, or if there is a motion like completely in zigzag nature, that is the turbulent in nature. But based on the physical property, like there is a non-dimensional number that is known as a Reynolds number, which is the ratio of viscous force and inertia force. And based on the values of the Reynolds number, you can again define the fluid flow, whether it is laminar, transition, or turbulent in nature. So if the Reynolds number is less than 2000, if it is 2000 to 4000, transition. If it is more than 4000, it is turbulent in nature. So you can define then the compressibility. Based on the compressibility property, I have already explained that you can, if the fluid is a compressible, then flow is a compressible flow. If the fluid is incompressible, then it is an incompressible flow. Then you can see the different, then again you can see the nature of the flow, which is if there is a rotational velocity or angular momentum is there, or you can find out if the velocity of the fluid is not in horizontal or vertical direction, there is a chance of the backward flow or turbulence in the nature. You can find out there is a angular velocity. And again it is the concept of vector calculus, and in the vector calculus that three different operator we are using. One is the gradient, another is the divergence, and third is the curl. So third operator, curl, is important to describing the flow, whether it is a rotational flow or irrotational flow. So when you have the expression of vector field or velocity field or velocity vector as a q, and you find out curl of q, if it is 0, then it is irrotational. If curl q is not equal to 0, then it is a rotational, means there is a angular velocity. So vorticity and other things you can define based on the rotational and the irrotational, and the same thing you can find out the gradient. So vector calculus, when you are working on the fluid dynamics problem or any physical problem, vector calculus, three operators are very important, and their theorems also, to solve the theorems like Gauss divergence theorem, and other theorems are Green's theorem, Stokes theorem. Okay, so all these theorems when you know, then you can easily see the mathematics at standard level as compared to the engineering people who are working in the fluid dynamics. They are using the mathematics. So as a mathematics, you can think how much mathematics we can involve and how much integration or vector calculus or operator we can use in our physical phenomena, and see that the complexity nature of the our problem. So this is then one dimensional, two dimensional, that is based on the dimension, viscous, inviscous, based on the viscosity you can define, and then you can see that the internal and the external force. Internal force means external force. You can see the example of water is flowing through the river. There is no boundary. That is the air is flowing. Okay, there is no boundary for the airflow. Or the case of, for example, of aerodynamics, you can see most of the gases flowing in the environment. There is no boundary. But if such liquid or gases moving or flowing in the closed regime or closed vessel like pipe flow or tube flow or capillary flow, where the tube or pipe or capillaries are completely closed. Okay, so that is the case of internal. Or human body example, you can see various type of flows are there, biological flows are there, and most of the biological vessels are closed. You cannot see that the blood is flowing outside. Okay, so that is the example of internal flows. So internal and external force based on the geometry. That's why I am telling you that most of the things are defining based on the physical property. Most of the things are defining based on the geometrical property, and their interpretation you can do based on the mathematical equation or mathematical model. So this is then the compressible flow regime. Basically aerodynamics or compressible fluid people they are doing, and that is again based on the Mach number, that what is the range of the Mach number. Based on the value of the Mach number, you can define the different category of the flows like subsonic, transonic, supersonic, hypersonic, and then again open channel and the closed channel, like whether your channel is closed or so this all categorization are based on the geometry, so that you can define. And again you see the another category of the flow, like when you apply the external force. Okay, when you see the example of the water is flowing in our home, like filling of the tank which is located or situated at the top floor, and when we are using the pump at the ground floor to deliver that water in the tank or to fill the water in the tank, that is the case of the force flow, because we are applying the force. Okay, and again when you see the river is flowing, okay, there is a force, gravitational force, but this gravitational force is a natural force. Okay, so that type of, or inside our body what type of flow, like blood flow or urine flow or other cases, so that is the natural, where we don't have to use the external forces, or we don't have to use external energy or any external work for flow. That flow is internal. If you have to apply, that is external, based on the different properties. One of the properties we have discussed, like viscosity and the relation of the viscosity and stress and rate of deformation. But if it is non-Newtonian in nature, then we can define based on the plasticity nature, based on the non-linearity, and based on the elasticity also. So we can define again the non-Newtonian fluid based on the time dependent and time independent. So time dependent means if the fluid behavior can be measured with respect to the time. So if time is again a parameter which is affecting some properties, like when viscosity is changing with the time, or viscosity is not changing with the time, because in the fluid the major part or most important property is the viscosity, and based on the viscosity many things we are defining for the fluid. So when viscosity is changing with respect to the time, that type of non-Newtonian fluid is known as a time dependent non-Newtonian fluid. And when there is no change in the viscosity with respect to the time, that type of fluid or non-Newtonian fluid is known as a time-independent fluid. So most of the non-Newtonian fluids which we are considering in our model, those are time-independent fluid model. But two different type of category of time-dependent fluid models are there, where you can find out, see, the tau is equal to the mu, and f is the function of this, that is for the non-linearity and the power law fluid, and this is the category of time independent, because here viscosity is not changing with the time. So this power law fluid model, which is the more general non-Newtonian fluid model, is time independent. So when we talk about the time independent fluid model, we have many, okay, time independent. So when we talk about plasticity nature, you can see I have already explained that if there is a plasticity, then it start deformation later, and due to the plasticity behavior and the concept of yielding stress will come, and you can easily see. So all this category we have already defined, you just see, and these are the some general model of viscoplastic fluid, where you can find out the different models which are available in the literature, and you can use in your problem for defining the various fluid or various fluid problems, like having the plasticity behavior as well as viscous behavior. So you can see that how much model, and one of the model which I have discussed, the linear model like Bingham plastic model, you can see that it is very close to the mathematical equation y is equal to mx plus c, and other equations you can see that. So depending upon your material or depending upon the fluid which you are choosing, you just try to match like which particular model will be more applicable. That particular model, if you can take or consider, that will be more interesting, and the result will be more. Then another type of non-Newtonian, that is based on the elasticity, and the concept of elasticity comes from the Hooke's law. Like when you apply the stress, the difference between the Hooke's law and the Newton's law of the viscosity is very small. Okay, you can see in the Newton's law, tau is proportional to the rate of deformation, and here tau is proportional to the deformation. So when tau is proportional to deformation, there is another proportional constant, and that proportional constant will come in the picture is known as the Young's modulus, and the Young's modulus is representing the elasticity behavior of the material. So when the elasticity will be more, then the fluid will be towards solid in nature, and if viscosity is there or dominating, then the fluid is towards the liquid. So you can see that we have the different model of here the spring is representing the elasticity nature, and the despot, this is the despot, and the despot is representing the viscosity in nature. So when you make the combination like the electric circuit, in the electric circuit we are doing the parallel combination and the series combination of the resistance and the capacitance, and find out the resultant resistance and the resultant capacitance, and we are measuring the how much resistance will be there in complete circuit, and what will be the best combination of this resistance in our electric circuit. So same thing, we can use the different combination of the viscosity and elasticity as a spring or as a despot or as a Hooke's principle or as a Newton's principle, and think about the different model. So when we make the parallel combination in the series combination in the first model, where spring and the despot in the series, and another case when the despot and the spring is in parallel, we have two basic model for the viscoelastic fluid. One is the same thing is applicable for the viscoelastic material also. So material science people, they are using this model as a material. As a fluid dynamic person, we are using as a fluid. So when we have the Maxwell model, so when we consider the Newton's law of viscosity and the Hooke's law, and make the linear or make the series combination, we have this model where the tau is stress and mu is viscosity, gamma dot is the rate of deformation. You see it is the time dependent stress, and lambda 1 is the relaxation time. So in the viscoelastic fluid, the time which is taking in make the original shape. What is the elasticity? When you compress any elastic material, after some times you find out it will take the original shape, right? That is the like spring. If you can compress and just you leave, you can find out after some times it will take. So the time taken to find out the original shape, that time is the relaxation time. That's why it is known as a relax. Okay, you are compressing, it is under pressure. When you are leaving, it is after some time relax. So the time taken to make the material relax, that is the relaxation time. So when you can define in such a way, you can find and see that in the first model we cannot find the elastic property in the first, only the relaxation time is there. That's why it is the viscoelastic. But in the second model you can see that there is a K, which is the Young's modulus. Due to this K, it is more elastic. So Kelvin-Viollet model is more useful when you are defining any material which is a viscoelastic material. But for the fluid problem or viscoelastic fluid problem, you can consider the Maxwell model. And again the extension like 2 spring, 2 despot, in series, in parallel, in mixed form, you can consider. And when you consider, then there are several models which you can find out. See the generalized Maxwell fractional, this is okay. Some models, okay, this figures are representing the generalized form like Jeffrey, Burgers, Oldroyd, B, second grade, first grade, third grade, fourth grade. I have not listed maximum, but there are many fluid models which are having the viscoelastic in nature. And then again you can use the application of the fractional calculus. The people who are working in the fractional calculus, now there is a demand. Earlier there was the problem, many people are criticizing that what is the geometrical and the physical interpretation of the fractional derivative or fractional integration. But now this people are accepting because there are some application, but still there is a challenge for the geometrical interpretation. If you can able to define the geometrical interpretation of a fractional derivative, it will be one of the novel interpretation, and you will get Abel prize or field medal. You know, in the mathematics, what is the highest level of medal or award? That is the Abel prize. Okay, and it is given in the International Congress of the Mathematics, that is ICM. Okay, and ICM is organized by the different organization or different country after 4 years. Okay, like if it is organized in 2022, so next ICM will be held on 2026, where all the big award of the mathematics will be given. If your contribution is good and your age is under 40 years, okay, you can be eligible for the field medal. But if your lifetime achievement is there, there is no age restriction or age gap, you are eligible for the Abel prize. And these both prizes are given in the ICM. It is organized every 4 years. Okay, maybe next ICM will be in Brazil. You can check it, ICM 2026, and they are also supporting the financial support. You can participate at least in one ICM. Even you can find the international travel support from the SERB also. Now it is ANRF. Okay, there is a support for the young researcher. You can get every fund, like for registration fee, visa fee, travel, accommodation, everything you can find out, and you should try once in your PhD. After publication of 1 or 2 papers, if you have 2-3 papers, then it is good to get that fund. So that type of knowledge should be there. So what I was talking like fractional calculus. Okay, so fractional model, now people are having the application when the transformation from one state to another state, or from transformation from one domain to another domain. Okay, and they are describing from 0 to 1. Like if it is 0, then it is one state, and if it is 1, then it is another state. So they are using the concept of the Boolean algebra from 0 to 1. The value of alpha is ranging from 0 to 1, and they are describing the model, different model, like as a fluid model. You can see the fractional model as I have shown. Like a fractional model, you can see like alpha is representing the value from 0 to 1, and when the alpha is equal to 0, it will be the model for viscoelastic fluid. But when alpha is equal to 1, okay, it will be more towards the solid in nature. So when alpha is equal to 1, then fluid is a solid, and when alpha is equal to 0, then it is more liquid. In between 0 to 1, there is a transformation from liquid to solid and solid to liquid. So this is the transformation or transition state, where from one state to another state transformation can be easily defined through the fractional derivative. But still, as I told, that the geometrical interpretation, like we can define dy by dx as a tangent, as a slope, okay, and we can also use to define the geometrical shape, whether the shape is your convex, concave, or finding the maxima and the minima. We are finding the critical nature of continuity. So all these things you can use the derivative, okay, simple derivative, and find out. So many geometrical properties you can use the derivative, but the fractional derivative, if it is d half y upon dx half, okay, what will be the geometrical properties? How you can define this particular interpretation geometrically? So if you can, people are working, they are thinking. If it can, then it is good. Okay, so these are the different model where you can see, and as I told that if the viscosity is depending upon the time, you can again describe the different type of. So in the time dependent non-Newtonian fluid, only 2 types of fluids are there, and very few people are working on this time dependent non-Newtonian fluid. So when you consider this model, one is the thixotropic and another is the rheopactic. Okay, so rheopactic and the thixotropic fluids, and see that it is the property viscosity which is depending upon the time. In one case it is increasing with time, another case it is decreasing with the time. So this is another type of nature, and you can see that some models, I have not taken the expression for this model, but you can find where the people are working and taking the different fluid models in a different type of application and different type of analysis. And the one reference I have given you where you can see, and this reference you can find out this is based on the food products, and most of the food products you can find in the lunch, dinner, and for the animal foods, for the other living organs, different type of food products are there, and see that what will be the rheological or physical properties of those food products. And many people are working for their purity and their digestion purpose, which food is very comfortable for particular reason. That's why the different region are having the different food culture, and people are taking based on the environment and depending upon their water property. And when you are habitual from the Uttarakhand and going to another place, you can have some problem for few days, and again you can be habitual because your mechanism or biological system will adjust with the some properties. So all these things you can see that how the non-Newtonian. So in the food product non-Newtonian behavior, you can find out the different non-Newtonian fluid models. And then many people are working on the nanofluid. Don't take a picture. I will share this PPT. Okay, and you can have the clear. So don't worry about that. Okay. So we'll share all the PPT. Then Anuj will also share the all PPT. So this is the nanofluid, where you can see that the nanofluid properties, like when the conventional fluid or thermofluids, earlier it was known as the conventional thermofluids, are having some properties of thermal. So the fluid is always having the thermal properties. Without thermal properties you cannot, because you can see the temperature variation in any fluid, any liquid. Okay, so when this fluid with some nanoparticles, the concept of nanoparticles means you can simply relate the solute and the solvent and mix both and find out the solution. So same thing when some liquids or some fluid are there and you are mixing the nanoparticle, or you are making the suspension of nanoparticle in some base fluid, then it will be the nanofluid. And the purpose is to find out the heating properties or cooling properties. Heating properties or cooling property means change in the energy level depending upon our requirement. So when we need that the room should be very cold in the summer season, a room should be hot in the winter season, then we need the heating and the cooling both. So when we have to increase the thermal properties, especially the thermal conductivity, we can mix the particular type of nanoparticle in the base fluid. When we need the cooling, so another type of nanoparticle we can mix and try to see the decrement of the thermal conductivity as well as increment of the thermal conductivity. So as per our requirement we can do it. Then the scaling or transformation, as I told that scaling and transformation are very important in the physical analysis. When we have to do the physical analysis for any type of problem, so we can see that how can scale the physical quantities or physical parameters so that we can easily take the parametric values and do the analysis. For example, if this is the room and we have to make the structure of this room or any building, like the map and drawings are very important before starting any big building, and that structure can be shown only A3 or A4 size paper. So how they are doing that? So they are scaling. You cannot show 1 kilometer or 100 meter large length in a A4 side which is having maybe 9 to 12 inch length and width. Okay, so how you are scaling? Then we are considering that this 1 kilometer can be considered as 1 mm. Okay, so that is the scaling. Means larger scale we can scale in the smaller so that we can define. And the same thing we are doing in our UG and the PG level, when we are doing the experiment of the physics and the chemistry. We have the data, and then that data can be plotted as a graph by using the scale. Like we can consider like one of the box in the, what is that chart is known as? What chart? Chart is there in your answer sheet also. No. Small, squares are there, small square, then bigger. Sorry, which chart? There is a chart where we are plotting the graph. Graphs. Graphs are so okay. Whatever then what we are doing, we are scaling and plotting the graph for our complete data set. Same thing in the physical equation, we try to scale the dimension. We try to scale the dimension. Dimension means unit of the physical quantity. If dimension of any physical quantity, suppose force is having the unit of Newton, okay, then how we can make the force unitless or dimensionless. So we have to divide that force with same dimension, and the dimensional analysis or transformation you can find in the book. There are 3 different type of similarity or dimensional analysis. One is the geometrical similarity, another is the kinematic, and the last one is the dynamic. When you have to do the force similarity, that is under the kinematic. When you have to do the velocity or time scaling, that is under the dynamic. And when you have to scale the geometry, means length and width or diameter or area, that is under the geometrical similarity. So all those similarity we can use and try to make our problem more simpler. Because when you are considering the equation, mathematical equation, and try to simplify the steps or equation step by step, or using the mathematical method to solve the problem, you have to consider the dimensional homogeneity. Dimensional homogeneity is very important. Every step you have to check, means dimension of each term should be same. So when you consider the dimensional homogeneity at each step, it is very difficult and sometimes it will be not satisfying, then your problem will be unstuck. Okay. So what you are doing, first you can scale with the dimension, make all the physical quantity dimensionless. When all physical quantity will be in non-dimensional form or dimensionless, it will be just like a variables, like x, y, z. And when it is variable, you don't have to take care about the dimensional homogeneity. You can apply any approach, any method and solve it. So that is the advantage. Another advantage is when you are doing the dimensional analysis, the problem will become, or your governing equation will also become simpler, because after dimensional analysis you can take some assumptions. So when you take some assumptions, approximation, you can transform your non-linear problem to linear problem, or sometimes your problem which is in the non-linear but can be handled through some technique. So that is the advantage, and these are the some non-dimensional. These are the basic principles which are used in any physical problems. Okay, whether it is related to material, whether it is related to energy, related to the healthcare, or any type where the conservations are there everywhere. Okay, because as I told that the complete nature is based on the material, and if material is there, then there is a conservation, and if conservation principle is there, you can formulate. So there are some conservation, and the conservation principle is basically defined, neither created nor destroyed. So when we have mass conservation, momentum conservation, and energy conservation, concentration conservation, nanoparticle, and these all conservation, and it works on this principle. You can see that whatever the input we are giving to the machine, okay, and the same output we are receiving from the machine, if there is no change, the amount of input and the amount of output will remain same. That means the change is a zero, and when change is a zero, that means it is the conservation. And this conservation principle is applicable for any type of change, where it is a change in the mass, where it is change in the momentum, where it is change in the concentration, whether it is change in the temperature, whether it is change in the electric voltage, and such type of changes or polarization or motion of the ions. Okay, all changes you can find out from this principle. So this is the basic equation, and you can find out the equation like continuity equation, you can see based on the mass momentum, mass conservation. This is the momentum or Navier-Stokes equation based on the momentum conservation. Okay, and then you can find out the energy equation based on the energy conservation. So whatever the subject, even I am looking, even bioinformatics, you know, and you can find out after sometimes biocomputer science, like some of the biological, but bioinformatics is there. Bioinformatics, all the data.
There is a term for biocomputer science. It's called computational biology.
Computational biology is the computation of the biology. But I am thinking that what type of biology can be used for the computation, and they are working on that. So many terminology you can describe and find out. So here, when we do the biological study in the form of mechanics, in the form of fluid, it is biofluid, mechanics, biomechanics, because in the mechanics, as I told that the concept of solid and the concept of statics are there, so you can consider as a biomechanics. And a very important book of the biomechanics is written by Keen and Fung. You can search Fung, and very basic concept of the biomechanics you can find from there. So these are the basic system where in human body or animal you can find most of the systems. You can see that it is based on the mechanisms, and many mechanisms are involved in the system where you can find out the fluid flow, you can find out the biological fluid flow, and see that how complicated or natural or complexity are there in their flow regimes, in their mechanism, and in their structure. So the first thing is how we can geometrically define the structure. Then second thing is how we can mathematically think the mechanism, or how much physics are involved in this particular mechanism, and then we can think about the problem, like small part of the vessel we are considering or complete system we are considering, because when you are considering more phenomena, more mechanism or larger system, it is difficult to handle. But when you considering the small part and the small channel and some of the mechanism, then it is easy to handle. And see that first, which is very important, that is the circulatory system. And the circulation of the blood throughout our body, that is under the circulatory system, where the pump is there as a heart pump, and the heart pump is a natural pump. There is no external devices, and that's why you can see during the attack, if there is a blockage and this heart is not properly working, then we are pushing from external way, or we are giving some external force so that blockage can be opened, and then heart will start working properly. So if you have the knowledge like how much pressure or how much force is required to propel the blood, then you can think some external devices, think some external force arrangement, and control the complete circulatory system. So when you have the complete data set where the people are working, like if you have because different age group, different people, different personalities are having the different mechanism, different rheological property of the blood, and how they are. So it is not easy. Suppose my heart is pumping in different way, not different completely, but the range of their frequency, you can find out my frequency is different from your frequency, another frequency, and the rheological property of my blood is different from. That's why the bloods are categorized in different groups. Okay, and the same thing you can see that in different level, age group. like for the kids, for the adult, for the old people, you can find out. So it is not easy. So getting the large amount of the data and thinking about what will be the normal range for different type of people, different aged people, and think about how you can control such type of mechanism externally. So when we have the large amount of the data and when we think the external fitted chip or devices and control the circulatory system or control the complete circulation in the our body, that will be the another advantage. And you see one of the example during the COVID and now time also, that when the oxygen level is low, how it is controlled through the ventilator. So what is that? If there is an infection in the lungs, if there is an infection in the lungs or lungs is not properly working, or you are not taking the proper breath, then there is a disbalance in the oxygen level. What the level of oxygen should be there in our body, if it is totally disturbed from some disease or from some infection or from some issues, external issues, okay, then how you can control? So that when it is very serious or the oxygen level is very low, then the people or patient are recommended for the ventilator. And what ventilator is doing? The ventilator is maintaining the oxygen level, nothing else. Okay, so that if your oxygen level will maintain up to some time, in between some additional treatments are going on. So what type of disease or what type of infections are there in your body, if that will be recovered and your lungs will start working properly and your oxygen level start maintaining, then your ventilator will be removed. So if such type of devices, and now you can see in very young age, even in child, the cases of heart attack is coming. Okay. So if we can think about some external chip which can be used in every family, like if there is a sudden attack, you can use and maintain the heart pump level circulation for some times, so that people can be transferred from one place to the hospital. Because in the hilly region you can see, if there is a case of heart attack and reaching from Srinagar to the AIIMS Rishikesh or Dehradun hospital, might be possibility that life will be gone. Okay, so if you can think in that direction, then it will be very. So the concept of how the heart is pumping, how much pressure is generated, how much circulation should be there, how much purity will be there. If all data set will be there, then you can prepare the external heart which will work and provide the external some forces or pressure, so that it will be controlled. So this is one problem where you can see the structure. You take the different type of structure, because again you can see the nomenclature of this. And in biology, two different type of studies are there. One is known as biology is being studied as anatomy. Anatomy means nomenclature of the different parts, and it is very easy. It is very difficult to remember the names of the different part. For the this living organs, especially zoology, somehow it is okay. But when you see the botany, plants name and the botanical names of the plants, it is very difficult to remember. That's why I left studying the biology after 10th, because remembering the biological name is not easy. So that is under the anatomy. That is, but again PhD, it was given by my supervisor, you have to work in this. That's why I started again studying the biology. Then the mechanism. Second part is one is the nomenclature of the parts. Another is the mechanism or mechanics of the mechanics of the different parts. So mechanics of the different part is known as a physiology. So anatomy and the physiology, these two are the different branch of the biology where you have to study whether it is botany or zoology, okay, and think about what type of mechanics are involved, what type of phenomena are there, and then you can formulate mathematically and see. So these are some examples. Like second is the digestive, starting from the eating to the west exit of the west, the complete digestion and moving through the esophageal movement, stomach, digestion in the stomach, then the formation of the chyme and the movement of the chyme in the large intestine, small intestine, and how much structure, different structures are different, chemical reactions are there, physiological phenomena are there, physics are there. So you cannot consider everything in your mathematical model, but one aspect or two aspect you can consider in your analysis study and try to do it. Okay, and then other system you can see like filtration of the blood through the kidney and the waste as urine, and flowing urine flow through the ureter, then the breathing process as we discussed in the respiratory system, and then reproductive system. So these are the major parts where you can see the different physiological phenomena, and these are the overview. I think I should stop because we have to come again at 2:30 where we will